and it's not a closed field, it's just over that particular closed surface, just over that surface. Plus, we would have to evaluate the surface flux associated with the shaft, plus the surface flux, E dot dA, for the right face. And when you add all this together, it should be equal to Q enclosed divided by epsilon.
You want the flux on the right to be flux 3, not flux E.
Oh. Okay, so this is essentially what we're doing. Now, as long as we stay in this narrow little region, over the first surface area, this thing, E is not constant. E varies with distance away from the center. So we have a varying E relative to how far away we are as we go from the center of the face outward. But the angle of orientation between E and dA always 90 degrees. So this reduces to 0 because the dot product of these two is this way. E is a function of R. dA, as we evaluated over that whole surface, there's a dot in there, will always be equal to 0 because the cosine subtended by E and dA is 0. The angle is 90 degrees. And that's my justification. Even if it's radially increasing or decreasing, doesn't matter. It never actually crosses the face. There's no flux. So again, E's not 0, but E dot A or E dA is 0. So this term here does not play a part in our calculation. It feels almost like cheating. Because you know there's field there, but there's no flux.
Trying to visualize what you're talking about here.
If you're looking at the one face, relative to the center, E is radial.
Right. So to me, that's 0 degrees or 180 degrees.
No, it's 90 degrees, because for any chunk dA, and this is a cylinder, so maybe we'll pick a little chop that looks like this, a little square, dA. Small enough that it's kind of cornered, but if it's small enough, it looks like a little rectangle. This is pointing outward at a 90-degree angle with respect to the field that will be passing along it. The field stays flush. It never physically crosses out into.
I see it like this.
That's all I'm saying.
I don't see that that's 90 degrees. I don't understand.
Because dA is pointing out. It's the direction of the face.
Okay.
So it's this. There's your field. But the area is actually oriented this way.
You're saying the area vector is normal to the face?
Yes.
Okay, that's fine.
Okay. That's fundamental to the definition. That's okay. So as a reminder, dA or A in general has a magnitude of whatever dA is, but the direction is normal to A. What direction is it physically facing? Because that's the only definable direction. You can't define a direction along its plane because it's pointing in any arbitrary direction along that plane. So the only definable direction is outward. And it's the only way we can justify making it an area vector, if you will. Probably should put a 1 in here. But the bottom line is that it effectively washes out. Now we have the region along the shaft where R is constant. Because R is constant by radial symmetry, we're always the same distance away from the charge. The electric field will be constant at any given point relative to the surface area. So whatever the magnitude of the surface of the electric field is here, it's going to be the same at any point along the cylinder. And not only that, it will be directed radially outward or normal to the surface. Even if the surface itself is changing direction as you go around it, the orientation of E will always be parallel or pointing in the same direction as the surface face at that point. So the electric field E2 reduces to E dA. And I'm making the assumption that the cosine of phi, E sub tens dA, is always 1 because the angle is always 0. That's the assumption.
You say that again? Well, that's,
Okay, if we look at any given region, here's the center, there's R. So out here we can define some dA. And that dA would be related to R. D theta, or let's call it D phi, as we work our way along the shape of it. Here, I'll draw it out bigger. This is one region. So this length is R D phi. This length is D R. Or I call it dx. If you want to it's just this times the angle dx. But the direction of this thing,
okay.
90 degree to that, is pointing in the direction of R, because it's pointing outward from the center back to the line at that point. And E is always pointing outward as well. So E would be pointing at every point along this thing. It would have a constant magnitude, but E is going to have whatever its value is at R. It's also going to be pointing in the direction of R.
So it would be facing the right at 0 as well?
Yep.
Let me get to that one. Yeah, I'll make the same argument we made to the other side, absolutely. So, you know, it's real nice with revisionist history to say, oh, it's just this, and we can pick these surfaces. But it was pretty clever when they first, when this was first applied. I mean, you know, this is a nice little map. Well, it would be now if you weren't given an expectation and told just solve it with Gauss's law. Right? But especially back in the day, if you make this assumption that this seems to be true, and then you start applying it to different, you realize, oh, I've got to really think about it to set it up to demonstrate that. So on this side then, yes, E at any given R distance with respect to dA, and it would depend on where dA was along that region, will always be 0. So there's ultimately this whole thing is 0. There's a lot to say just to come to that conclusion, but it's important to kind of see why. It's not just because, it's not just because I say so, it's I'm trying to set the table in a specific way for this to be the case. All I want to do is evaluate it then. Okay, so then everything reduces. I'll close this start filling in the gaps then. And for this particular surface, the total efflux, which is P1 plus P2 plus P3, reduces just to P2. Again, it feels like you're almost cheating. It's like, how, you got three surfaces and you just, as long as you can define it properly, it's always true. That's the elegance of it. And so this quantity, which we can define now, and I already started to set it up, it's E2 dA2. As I evaluate this surface, this whole thing should be equal to the amount of charge enclosed divided by epsilon naught. And anytime you evaluate some quantity over itself, that's just A. In this case, it's just the whole value. So what we're left with then is E2, A2, is equal to Q enclosed, and to jump to the punchline, surface area is related to pi r squared, wherever I am,
Yes.
dx. Use d or delta, use d grid. And then we have the constant field associated with that r. So I'm going to write it as dr because it's the e associated with that distance r. Now the other side I've got Q enclosed. But I could write Q enclosed as the total charge Q divided by the length of the line. That's the amount of charge relative to any segment of the line. So all the charges along the line, the ratio of charge to length is constant, times the amount of charge, or the amount of segment I'm enclosing, which is dx. I can divide all of that by epsilon naught. And there's what's wrong with this. I already see what's wrong with it, but just, what area am I looking at? Let's just make sure we're clear about that. It's the side, which is based on the perimeter.
2 pi r, yeah.
So circle there for symmetrical pi r squared. It's pi r d.
Will you, I understand that Q enclosed is Q total divided by L, the length of, or Q enclosed is Q total times the ratio of dx over L. Yeah, I get it.
Okay, yeah, so this is, of the whole line, there's only this little segment, which is delta x. But fortunately, because it's uniform, the ratio of Q total to L will be the relationship, will be the same for any delta Q over any distance delta L.
It's just the linear density.
It's just a linear density, without necessarily having to define that extra term. It is, it's a linear charge density. And the reason I'm saying that is the charge is spread equally along this thing. So, if you look at it, we can divide through by the width. And ultimately what we're left with is that the electric field at any distance r, corresponding to this distance r, should be related to Q total divided by the total length. It's a ratio of that charge density. Surprisingly, dx cancels out, and we're left with 1 over 2 pi epsilon naught. And again, you start to see all these reasons why using Coulomb's constant, what K is not always as useful as just using 1/4π. And sometimes we write this as lambda over, oh, we did something, I have that down right now. 2π epsilon naught r. And that's functionally what we had here, and there is something else missing here. There's something out here, isn't there? There's a term missing there, isn't there? Maybe there isn't, but it seems like there's a term missing there.
Is it not gonna look the same in the book?
It should look the same in the book. Is that what it looks like in the book, specifically? I don't know as it is. It's in an example. Sorry to make you have to look for an example in one of the examples, but it's in an example. Line of charge.
We got lambda ds over 4π epsilon naught r squared. We've got dq over 4π epsilon naught r squared.
Its equation,
The 2312?
it's 2221
22, 21.
on page 642. It's in the lecture notes too, by the way.
Do you have a different edition than I do?
Probably. You have this edition?
Well, yeah.
Okay.
The 22, 21
Well-
on 642 is 1.73 lambda.
No, go up a couple, okay, it's in that line, don't be quite so literal, it's in that line a little bit higher. Oh no, is that still the line of charge? Nobody kept notes on that, really? I mean, I can derive it, but nobody actually kept notes on that?
I thought for sure I wrote all this stuff down, but I don't know.
I mean, really, I was just planning on you guys having it so I didn't have to rederive it, because that's 10 minutes of getting my coordinates straight and clearing up two minus signs, I guess. So this is clearly not right, and I can tell because the units won't work out, for one thing. And even beyond the units not working out, I'm pretty sure there's an R here on the outside. But I don't want to make, like I know there's an R there. I always hate just making assumptions when I haven't fully looked at it. Because then,
Oh, is that why it's on the worksheet?
Yeah, on 10, that's right.
is it Q over 4π epsilon naught R times the square root of L squared over 4 plus R squared? X, Y, I think I used Y. Come on. Let me see it. If you wrote it down, I'll translate it. Is this the line of charge? Yes, it's right there. No, right. Well, we transferred that into Y. So I've acceptable here. So it's this. It's a 4π though, correct? Okay. So Q total is another way of saying lambda L. So I wrote it in one of two different fashions. Okay. I wrote it in terms of charge density, but functionally it's this. And if we weren't comparing, I guess it wouldn't matter, but it would be lambda. I think I wrote it in this way. Now, this is what our solution is if we solve it directly using Gauss's law. This condition is the condition where we'll just make a note, when L is much, much larger than R, then this thing reduces to this. Because this thing, the L comes out, this term goes away. And this thing starts to look like lambda over 2 pi epsilon naught distance away. So you can actually solve for Gauss's law, or using Gauss's law directly, as long as you make the conditions consistent. The alternative, by the way, there's another simple alternative to this. We could make a cylinder so large and so far away that this thing reduces to a point charge as well. Again, it feels like it's cheating, but you can do so. Point is, this is a lot easier to solve if you see it or if you memorize, you remember it by a long shot than setting up those components, justifying cross terms cancel out so you don't have to deal with the y component, the side component, and then solving that integral that has a L squared over 4 plus R squared raised to the 3/2. Remember that? It was not a pretty integral. This is pretty straightforward. So that's essentially the key to these problems, and when you can use Gauss's law. So let's take a break. That was 20 minutes of finding that equation, and 10 minutes I didn't expect to have. So let's take a break and come back and look at its application to a couple other practical examples.
No, I've just been going, I've been having
When
this
L
habit of,
is much, much
just
larger
going to the store over
than
there,
R,
and I
L
just pick it up,
squared
usually like in
will
class.
so diminish R that this term basically vanishes.
And then during the worksheet, we obviously know that L is way, way smaller than R.
Then the R comes out.
That's right, you talked about that first day.
Copy?
Of what?
This position is upside down, maybe.
Probably, yeah, this is probably the
Just
upside down
kind of see what you think
position.
about it, because there's, these things you start seeing when you can apply Gauss's law, in this case, maybe it was not quite so bad either way, at least in the sense that when we applied Coulomb's law, it was at least solvable. So it wasn't horrendous, maybe a little bit easier to solve with Gauss's law, if you can figure out the intuition to do so, or have seen the process. But there are examples where it isn't so obvious. So let's think about an example, and an example might be, let's take a flat sheet of charge. Now, there are two different flat sheets. There's the round disk of charge, but I don't know, that's kind of.
What makes it disk of charge?
I guess we can make it just, it's still a flat sheet, but it's just a surface area. Okay, so here's very, very thin. And let's make it conductive. So this sheet of charge has a certain radius, r. And the question is, if we were to be a certain distance away from r, or I'm sorry, from this sheet, give this thing a certain amount of charge. What is the electric field at some point out here? And to make life easy, let's just give a coordinate system, x and y. So we can call this, and z would be out of the board. So we can call this E as a function of x. Not as general as I like, but we can sort of do that. So, and to make it a little more palatable for what we need, we'll start by assuming that that we're looking directly from the center outward. And we could even say right, left or right for a certain distance x away, right? From the center of the disk.
Is that a point to the left, that your little arrow coming in the center?
Yeah, this is the distance here. And then we're just some point out here.
And that's what we're concerned with, is
Yeah.
the field at that point.
We could do it over here, we could do it over there, it's just you stop losing even symmetry for Coulomb's law. So let's just look along the center. And let's assume that the magnitude of this distance, x, is relatively small compared to the radius of the disk. And Q disk is uniform. Distributed is the technical word, but let's just say spread out. And let's assume that this thickness is approximately 0, or at least super, super thin. So let's just say it's negligible. It's there, but it's not real, real thick. So, first of all, I guess I should fill in this. There's charge on both sides. It's a conductor, right? So it's not all on one side, only half of Q is on either side. Total Q spread out on both sides. Does that make sense?
Since this thickness is so negligible, it's
Well, it's still gonna be split out on either side, it's not gonna be on one side, you still have opposite sides.
Well,
Mm.
I'm just saying, as if it doesn't have.
Oh, in other words, yeah, so you don't have anything spread out along the sides.
Hmm.
So yes, and let's maybe make this a different color so it's a little bit more. Intuitive to see the charges. So, and you got charge on both sides. How would we solve this problem? What would be a reasonable symmetry to solve it?
Sphere large enough that treat it as a point charge.
Always, always. As long as we can sit out here somewhere, always. But if we can't sit out here somewhere, if we're in close relative to the dimensions of this thing, then probably the best surface might again be a cylinder.